Hmm.
Yeah, sorry, I didn't announce the title, but you're doing it yourself.
Yes, this is the title of my talk, I think. Okay, so this, well, given the topic of the conference, this might be more of an entertainment session. But well, there's amplitude, so it's very amplitudes motivated. And if you wish, I'm going to tell you about gravitational waveforms of the whole universe. Okay, the whole universe is like breathing and like you know, vibrating at its very early stages, and we try to understand the patterns of the cosmological correlations that are set at the Big Bang. Okay, so that's the connection. So I need to start by telling you the final answers so that then you either follow or decouple. Hopefully you follow and find it interesting. So I'm going to tell you about a toy model of the early universe. Which consists of a single field. I can't do spin 2, it's too complicated. Okay, so gravitational waves, too complicated. So it's a single scalar. That's fine because those are the only things we measure at the moment. We measure scalar waves from the early universe. They're responsible for the formation of structure, density perturbations, and that's the sort of the reason why we're here today. So it's a toy model because this scalar is not realistic for structure formation. More technical level is conformally coupled. Conformally coupled meaning that I adjust its mass to the Ricci curvature of the universe. And I'm going to make it self-interacting at weak coupling. Meaning I do three level stuff. That's already going to put me in a lot of trouble. But I'm going to relax the assumption on the cosmology. So I'm going to make the cosmology. So typically we're interested in some FLRW type of cosmology for the early universe, more or less well approximated by de Sitter space. If we want to set up the initial conditions of something like inflation and so on. But it's a toy model. I'm going to take a power law cosmology. And I'm going to write that the scale factor is a power law of conformal time. And I'm going to write it like this, 1 plus epsilon. And this epsilon is going to make an appearance that is very familiar to people that work on amplitudes. And just for my embarrassment, I don't remember, but epsilon for integer, negative integer values are more or less all interesting cosmologies. So epsilon equals 0 is de Sitter space, so inflation more or less. -1 is a flat space in us. And then -2 and -3, I always get confused. One is matter domination. The other is radiation domination. It's an exercise of the reader to figure out which one is which. But all interesting cosmologies fit into this framework. And within this model, I will tell you some machine that allows you to compute any correlation function. Okay, so here is the setup. So time goes up. Unlike gravitational waves from black hole merger, in which you can see the detectors go vibrating and you see a waveform in time, you only have a static pattern of density perturbations that is set up at the hot Big Bang, and you need to, they're stochastic. It's an interesting stochastic process. So there are some, some thrust and some peaks and so on. They have some interesting correlation functions. And I would like to compute these correlation functions as coming from causal time evolution within this model. So for example, if I Delete this. If I want to compute like well, 2-point function is just free propagation, that's boring. But then maybe there's a 3-point correlation function that comes from self-interaction, some 4-point correlation function. Then the 4 points, interesting things can start happening. So you can have self-interaction like this, or you can have some exchange diagram like this. And you can do like crazier stuff at 5 points, 6 points. You can draw Feynman diagrams here in the book. And you'd like to compute these cosmological correlators. Okay.
Of the scalar field.
So the scalar field at fixed time. So say let's take, for the sake of the argument, some accelerating cosmology close to the center. So I set conformal time to be very small. Set it to 0, very small conformal time, and then I compute a correlation function. Say, let me call the scalar field var phi. So I compute var phi of x1, var phi of x4 at fixed time eta that I set to 0. So the question is, how do you compute this? It's kind of tricky to do in cosmology. And I'm going to tell you some machinery that is inspired by Amplitudes that tells you how to do it. And the final results, to make you excited or bored for the next 40 minutes, is there is a picture that is intrinsic to this surface. That's why the title is The Emergence of Time. So you can do an operation that you just move these points around. This is a static pattern. And then this correlation function is going to change its amplitude. So meaning there's some differential operator that depends only on x1 but not x4. For example, annihilates this phi to the 4th thing here. And I'm going to tell you systematically how to find it. And you can essentially explore the final diagram by just anchoring yourself here to this late time boundary. That's why we call it emergent time, because, well, hopefully it should be straightforward. The reason you just have access to these fixed static positions, you can move them around and see how the signal changes. It goes up and down. And there's some differential operator that will annihilate this correlation function. And I'll explain to you how to find it. And I'll explain to you how, as you take derivatives of this correlation function, you really explore the Feynman diagram, you discover the underlying time evolution.
Sorry, very nice question. So why might be interesting to the operator that annihilate that kills that correlation function? What is?
Well, because then I'll be able to solve for phi up to a few constants that, and I know the boundary conditions of the problem, then I'll be able to fully fix it. It's so let me.
So that is somehow independent on the dynamics of the Lagrangian thing?
No, it is dependent on the diagram. So this operator here depends on the specific thing you're drawing. Okay, so if it's this, you'll be some operator, and so there is some picture for depends on the theory and so on. So the only it's a bit like the following. So you have to do time integrals if you come from old-fashioned perturbation theory. You need to do time integrals of the insertions of these vertices, and I can change the question and find a differential equation that the integral satisfies. So that's it. So that's the story.
So what time is 0 for epsilon equals 0?
No, for any epsilon, it's functional epsilon. This is very schematic, but I'll make it clear in a second. Yeah, this will be a major anyway. So this is a cartoon. I'm going to tell you the details. Okay, so that's it. Any questions? So why? Well, maybe I should, given that people are interested in gravitational waves from mergers, I should tell you why we care about this. Well, there are a few reasons. One is conceptual, like we think that time, whatever, breaks down at the Big Bang. And we know from string theory, for example, from holography, that probably this notion of time will emerge from some different type of questions. And here we're trying to use this philosophical clue coming from ADS-CFT to try to ask questions that are intrinsic to this late time surface. This is also where we can, with our standard model of cosmology, push the clock backwards. We can't really continue running the clock backwards beyond this reheating surface. Okay, so the actual timeline of the universe, if you take this black surface down here, the actual timeline of the universe is such that time goes up. Then we sit here, now there's usually a draw with blue, but it's global warming, so I guess that will be fine. And then there's CMB photons that are emitted somewhere here, and there is a galaxy clustering that happens much later. And from these tracers, so there's the CMB fluctuations and the galaxy clustering. And from these, we can trace the statistical distribution of these primordial perturbations. We can run the clock backwards. We think we understand physics reasonably well, all the way to very close to this black surface here, and it will give me rise to the statistics of these files. Okay, now, full disclosure is that all the data we see in the universe right now is well explained by the Gaussian approximation. So if we have just a 2-point Gaussian random field that's almost scale invariant, that would be enough to explain everything we see. But we do believe that the process that gives rise to the initial conditions being set up is non-Gaussian intrinsically, and we would like to understand it. Okay, so there's a phenomenological vein to understand the general physics of non-Gaussianities, if you wish, waveforms and the ripples of this early universe, and also something more conceptual to understand the emergence of time. Okay. Yes.
How sensitive are initial conditions, like choice of bunch
You will appear as a boundary condition in the solution of the differential equation. So if you change from Bunch-Davis, you can incorporate it. Typically, if you change from Bunch-Davis, it's easy to incorporate, and it makes a dramatic prediction that is ruled out almost immediately. So experimentally, it actually predicts that the signal in a certain kinematical regime is very large. So for example, if you take the points and you line them up, so if you take, for example, 4 points, you take a configuration like this, okay? They are lined up, 3 of them, this collinear limits. In non-Bunch-Davis initial conditions, you become very sensitive to what happens at the beginning of inflation. The signal peaks, blows up, and then you have to jump some hoops to keep this phenomenologically viable. In Bunch-Davis, everything is smooth. There's no singularity in the physical sheets, and then hard to detect, but everything is sensible. But short answer is it's in the boundary conditions of the differential equation. Okay. Very good. So let's do it. So the mathematical tool to tackle this problem undergoes the name of twisted cohomology, which is a fancy name for something trivial. So let's see, twisted cohomology is a very systematic way of taking 2 things into account. One is integration by parts, and the other is partial fractions. So let me explain why I need this mathematical tool. So we start modest. We just go back to the drawing board and look at specific diagram and try to write the actual time representation. Okay, I said these fancy words about emergent times, but let's just go back and write the down-to-earth mathematical expression which time is integrated in. So I will explain to you how it works in this simple example here of a single exchange. If it's contact, this model is just too simple. Okay, so as an aside, people ask me, what about contact? So here, it's essentially a power law in the kinematical variables. So it's just too simple. It's you're killing a fly with a cannon. So there's no reason to focus on this example. Maybe I'll just write it down to introduce some notation. So it's convenient. Remember, it's FRW cosmology, so FLRW. So this is the scale factor of the universe. This is the metric. So there is a translation invariance. It's convenient to go to Fourier space and talk about Fourier modes, a spatial Fourier modes. There's no conservation of energy. Importantly, it's cosmology. Energy is not conserved. Even in flat space, the energy is not conserved. It's as if instead of computing an S matrix, you just decided that t equals 0. I'm going to measure everything at equal time. So you will measure particle production. You just slicing the vacuum bubble diagrams and seeing the particles that being produced instantaneously. Okay, so this diagram makes sense even in flat space, just not related to an S matrix. So for this, so the technical reason why it's useful to tune the mass of the scalar is to make all mode functions simple. So all mode functions of the scalar field are essentially plane waves up to some redshift factor, the 1 plus epsilon. So that when you write epsilon equals -1 flat space, you go back to the usual massless scalar plane wave. K. Okay. Okay, so then it's clear that if I have, for example, some cubic self-interaction, here's some G5 cube, then there's really not much to do. You integrate time in minus infinity to say some eta naught, or let me make it 0. And then there's going to be some redshift factor, eta to a certain power, but then each mode, K1, K2, K3, just contributes with a plane wave. So just by dimensional analysis, this is just going to be some power law in K1 plus K2. So there's nothing particularly exciting in this example.
Positive power law.
No. Yes, in epsilon, positive, it's epsilon, in fact. So that when you set epsilon equals -1, flat space becomes a simple pole. Okay. And epsilon equals 0, the zeta, it's a logarithm. As usual, power to the 0 is log. Particle physics. So anyway, so this solves the differential equation, but the differential equation, let me call this x, which is related to the total energy flowing to this vertex x. X is just K1 plus K2 plus K3. It solves the differential equation, this correlator, but it's not terribly exciting. The differential equation is the differential with respect to x of psi is epsilon over x psi. Okay, not incredibly illuminating, but let me write it. Let me be pedantic for a second and write it like this. It's epsilon d log x psi. Okay, so okay, I'm doing nothing here, but it will be useful in a second. So this was a baby step. Now let's do this example. Is this? Yeah, please interrupt me, okay? I go fast so I can show some meat, but I'm happy to stop and discuss the more general aspects of the problem. I have 15 minutes. Let's do this example now. Now this example is actually tricky. Okay, first of all, I tell you there is an explicit answer for this example. It's a sum of hypergeometric functions. It's not a power loss. The example is not trivial. Okay, you can still write it in closed form. So now there are two times that you need to integrate, and there's some propagator here. So the general structure is going to look something like this: integral dx1, dx2. There's going to be some mode functions. This k1, k2, k3, k4. Again, now let me call the sum of these momenta that flow into this vertex x1. This sum here I call x2, and the exchange momentum I call y1, 2, because it's easy to generalize to higher power. So okay, it's going to look something like this: e to the I x1 plus y1, 2 plus e to the I x1 eta 1, e to the I x2 eta 2. There's some propagator that depends on y1, 2, eta 1, eta 2. Okay? And some measure factor. 1, 2. Some power. So now let me be slightly more explicit, and I'm going to reverse Schwinger parameterize the exponents. So usually in Schwinger parameterization, you take the denominator and throw in the exponents, but nothing stops you from doing the reverse. So I'm going to take the exponents and throw them in the denominator. There's some final parameters, dx1, dx2. And long story short, there's a nice, beautiful geometric way of understanding all of this that undergoes the name cosmological polytope. Let's do Arkani Hamed, Benincasa, and Postnikov. You can look at it if you're interested. This is the answer, and hopefully this will become familiar to people who work on Amplitudes. So this is a function of three variables: big X1, big X2, and y1, 2, and it has this integral representation. And I find it extremely cute that epsilon plays the role of the dim-rag parameter in amplitudes, and it's a product for propagators. It looks like a loop of amplitudes. Okay.
So these represent only the exponential or also the green function?
Say again?
This is a representation of only the exponentials?
Everything.
Also the green
Yeah,
function?
yeah. Because I tuned the mass. So the green function is a bunch of exponentials. That's why I tuned the mass of the scalar. So in the end, there's a sum of products of various exponentials that you can repackage and recondense here. And yeah, in fact, well, this is a parenthesis for the aficionados. This you can also rewrite like this: the x1, the x2, and then there's a measure, and then you write the flat space answer for the wave function where you shift the xi to xi. Meaning that this integrand here, this rational function, when you set the little x's to 0, is the flat space answer. So if I did the computation in flat space, the answer is literally this: x1 plus y1, 2, x2 plus y1, 2, x1 plus x2. Okay. If you're, where is my 1 over s, the usual Mundell sum? If you send the sum of energies to 0, you sit on the support of the standard flat space scattering amplitude. You see that as I send x1 plus x2 to 0, this becomes 1 over minus x1 squared plus y squared, which is the Mundell sum, if you want to. Okay, so you see there is a way of relating this to the flat space scattering amplitude. And anyway, so I could spend a lot of time talking about this. Move on. There's another cute thing here that, well, this formula should make sense for epsilon equals -1, which is flat space. And I just said that the integrand is the flat space answer. So how can it be that when I set epsilon to -1, this integral goes to infinity? How can it be that this becomes just a rational function? But lo and behold, it does. Okay. So there's it has logarithmic singularities, but you do wave function normalization and you get the right answer. Meaning if I solve this a generic epsilon and set epsilon to -1, that's going to be something divided by epsilon plus 1 squared times this right answer. Okay. So everything makes sense. This is an interesting function in the series space. It's a dilogarithm, and for generic epsilon, you can write it in terms of Gauss hypergeometric functions. Okay. So now comes the twisted cohomology thing. So what is the idea? The idea is that if I take, I want to find a differential equation satisfied by this. And when I take the derivative with respect to either big X1 or big X2, y12 I can just pull out and just set the scales. There's really only two variables in the problem, big X1 and big X2. I'm going to generate some denominators here, but then I can partial fraction and integrate by parts. So it seems that I'm not making progress because every time I take a derivative, I'm increasing the exponents here, but sometimes I will through integration by parts and partial fractions. And the crazy thing about this procedure is that if I keep iterating, at some point, it halts. Meaning I take a derivative, I get back the same thing I started. Okay, that's why it solves the differential equation, this function. So this is a known, people that work on amplitudes, it's used even now in computations of gravitational waveforms. I'm going to give you a physical interpretation of what's going on. This I think is new. Doesn't happen in these other areas. So first of all, maybe to get a feel for how the method works, let me draw the integration plane. So I have to do an integral over little x1, little x2, and the integrand is singular or has a cut along 5 special regions, loci, whatever. So there are 3 lines related to these guys going to 0. So they carve up the plane like so. And then there are the lines at the origin. They are somewhat special because they have these factor of epsilon, these cuts. And in fact, that's why it's called twisted and not ordinary cohomology, because I mean, this introduces a cut, and as a good GMRAG user, it's going to allow me to throw away boundary terms at 0 or infinity. I'm going to do it like not caring about for a single second whether it makes sense to throw away the boundary terms and hope for the best when the settles. And the amazing thing is that it works. There are examples in which you know the boundary term contributes, but if you work a generic epsilon and try to go to those limits, you get the right answer. Of those crazy magics of physics. So there are, if you look at so these are the lines, the 2 extra lines. So you see, you carved up the integration plane in an interesting way, even though you're integrating only over this corner here. The fact that you carved up the plane in an interesting way tells you the way forward to solve this problem. So notice that this is a very special integrand. So if you look at these, I only have 3 components. If you look at the integrand, it's a very special, so the integrand is x1, x2 to the epsilon times a very special 2 form, the x1, the x2. This thing here is a very special 2 form. It's a logarithmic form that has singularity along the corners of this triangle. And it's essentially unique up to normalization. So this is called the canonical form. Canonical. So if I give you some bounded region on the plane, and it's a polytope, meaning that you just carve it with like planes, hyperplanes, and it's closed, then the claim is that there's a unique form that, well, top form if it's real space, middle dimensional form if it's complex space, that has logarithmic singularities at the corners and nowhere else. Okay, so it's a very special form, and that's the reason why there's this whole geometric picture behind these cosmological correlators. And it tells me that I'm going to have an easier time than usual in finding differential equations because it satisfies all sorts of amazing properties. For example, if I take the differential canonical form with respect to one of the kinematical variables, say dx1 or dx2 of a canonical form, it's a total derivative in one of the integration variables, xi, some other object. Very good for integrating by parts. So it seems that you're going to have a hard time finding out how to integrate by parts. When you start taking the derivative of this integrated object with respect to one of the external kinematics, and it's, oh, here it's trivial. For example, if I take a derivative with respect to big x1, it's clear that it's the same thing as the derivative with respect to little x1. So it always appears in this combination. So I'm automatically allowed to integrate by parts. But it looks like I'm not making progress because when I integrate by parts, I'm going to hit the measure, right? I'm going to hit the measure. So I'm going to pull some factors of 1 over x1 when I integrate by parts with respect to x1. So it looks like I traded an integral that I don't know how to do by another integral that I don't know how to do. So, but somehow the magic of this twisted cohomology business is that there's some mathematical theory that shows me that this procedure will stop. How long does it take until it stops? The very easy counting problem. You look at this figure and you count how many bounded regions you have. So let's count. 1, 2, 3, 4. So meaning that if you take 4 functions that have singularities only along these special planes, and you form a vector with them, meaning if I take a vector, I take 4 functions. Let's take integral over omega x1, x2 to the epsilon, and then 3 others. Okay, I'm going to tell you in a second which 3 others. Then what happens? If I take a differential of psi with respect to this axis, then I'm going to move around and I'm going to get back something that is proportional to these vectors themselves. Okay, and this is the differential equation for you. No, I mean, naively, you would have thought that this procedure continues. I mean, I keep taking derivatives and I'm going to produce bigger and bigger denominators, but somehow the magic of this integration by parts and partial fractions is such that if I take 4 independent functions here with prescribed singularities only along those lines, and they're linearly independent, then if I take the differential, I just move around the space spanned by these integrals. Okay, and this is the matrix A that I get. Okay, so if you work on amplitudes, this should look familiar. Now all sorts of nice magic. Is this clear, by the way? If you're not following, it's time to ask. It's going to become wild. So what is the strategy? Let me reiterate the strategy. We want to find, so the integral is too complicated. The differential equation, I know how to solve. I solve around the point, I give the value of the function around the point, and I build it up locally, the solution. Very good. But now I have a complicated integral. I don't know how to find the differential equation. But the integral is only singular on some regions that happen to be lines. And then there's some powerful mathematical theory that tells me the following. I take within the, I could, for example, take for these other functions, I could have just changed the exponents here. I could have changed from 1 to 2. I could have erased this exponent. I could have put a 1 over x1 here. You would just produce other integrals that will be linearly independent from the original one. And then the theorem tells me that if I take the right number of them, in this case 4, related to the number of bounded regions, the procedure halts. Meaning I take the differential, I'm going to get some mass, but the mass is expressible as a linear combination of the original 4 functions. And that's very powerful. It means that now it's just linear algebra. If I want to get the differential equation satisfied by this guy, just linear algebra.
So sorry, but this passes. I mean, I can accept it, but it looks like magic to me.
It is magic. Yeah, it was developed by people that invented this generalization of the logarithm, like Moto and Concha, all like people like that in the 70s. I'm just telling you the answer. It is magic.
Okay. But I buy it.
Yeah, it is. It is magic. Yes, I agree. It is a very hardwired way of systematically dealing with integration by parts and partial fractions. But that's essentially all that runs in the background.
You need to know the singularities, though.
Yes,
Yes.
you need to know the singularity.
So you need to.
Yes,
Know the singularities.
but for this toy model, I know the singularities.
So, yeah.
This is similar to master integrals.
It is similar, but it will be much cooler because I'll have a physical interpretation for everything that appears here. In fact, I don't even need to build them. It will be generated automatically. But I'm
Mentioned that this 4 is because you have 4 bounded regions.
yes.
So you know why is that? That
I-
number 4 or 5.
An intuitive argument for that.
4 by 4. There's some combinatorial way that yeah. To be honest, I can't regenerate in my head at the moment, but it's 4 to the end for an endpoint. So for example, for this diagram here, 3 integrations, it will be 16. So for this, so it looks like we're gonna run into trouble very quickly because for this example, 64, how the heck am I gonna build 64 master integrals in a space? So here the space, there are 3 integration variables, there are 3 times. There are 16, I need to visualize 16 pieces of Lego in a 3D space that is carved by a bunch of planes. So clearly this picture runs out of steam very fast, but everything will, trust me, everything will be algebraic and you won't need to think at all to build the basis. I'm just building the climax. Yeah, and in fact, this is, yeah, for this example, you have different topology. You can use this. And same answer, 64.
This would be all hypergeometric, I guess.
No, here it's already a mess. There's some PDFA stuff and yeah, very complicated. Here it's very useful to take the flat space limits to, for example, it's a polylogarithmic. So this has Lie3 for the sitter, this has Lie4, the sitter. So.
But I think cosmological already 4-point function are hard to measure. Do we really need to do higher point function?
Oh, this, I think that the motivation to do this for phenomenology at 3 level is very weak. This, I think, is useful as a springboard to understand loops, which is a very murky, poorly understood problem in cosmology. So, for example, there are many claims that loop corrections overwhelm the 3 level contribution to inflationary correlation functions. And it's not clear when it's true, when it's not true. We would like, for example, is there a Passarino-Feldman decomposition of a 1 loop amplitude? We don't know the answer to this question. I think ultimately the most exciting question related to this is to understand when gravity kicks in, these quantum effects can become rather big, and you would have a systematic way of understanding eternal inflation. So these reheating surfaces start becoming bumpy, and you want to understand this high multiplicity correlation functions. For the purposes of measuring non-Gaussianity, this is way overkill. The most immediate application I would say would be to understand the structural loops. The 3 levels of complexity. So we're just trying to systematically understand 3 level better. Okay. So let me give you a couple of properties of the matrix A. First of all, the matrix A, if you, oh, so let me tell you, obvious guess for the basis is to integrate canonical forms associated to 3 other bounded regions. Could have taken this one, this one, this one. But even here, there's already a little puzzle because I can take regions. For example, I can take instead of this pentagon, I can take a square. It's independent of the little triangle. I could have done just that. So even here, there is still a little fishing expedition that you can go into, figure out what is the best linear combination. But if you take the canonical form associated to 3 other independent bounded regions, it's already very nice. So automatically, epsilon only appears here. The matrix A is epsilon independent. It's linear in epsilon. And it's very sparse. It's 4 by 4, but almost all entries are 0. So it's not a very complicated matrix. And it cries for some deeper structure going on because the entries are very simple. So now I want to explain to you, instead of showing a matrix that you'll forget in 10 seconds, I want to explain to you physical picture of what's going on. So let's try to build this matrix A systematic. So you take the original wave function, this is the integral of the canonical form of this triangle here, x1 x2 to the epsilon, and then you hardwire all the properties of canonical forms, etc. Now, if you take the derivative, for example, only with respect to x1 of psi, what will appear on the right-hand side is the following. I'm sweeping all the technical details under the rug, okay? You can come and ask me later. But what will appear on the right-hand side is the following. You get back psi itself times 1 over x1 plus y over 2 plus psi minus. So you get a new function. So you get back something that so f is again. So the reason why this f is unambiguous is because f is the integral of another canonical form times x1 x2 to the epsilon. So that's why I can cleanly define it. And the denominators that I generate are interesting. I get x1 plus y12 and x1 minus y12. So this uses a mathematical machinery. Let me go back to physics. Let's draw the diagram. It's x1 here, x2 here, y12. And I took a single derivative with respect to x1. So I'm just wiggling around these points here. So I'm going to try to explain to you how time emerges from the picture. So I'm just wiggling around these points here. And I'm generating denominators, singularities that are associated with the energies that flow into the left vertex. Okay, I have x1 and y12 here, and I'm generating only x1 plus or minus y12. Related to the question of Bunch-Davies, you see, when I send x1 to y12, it's trouble because this is completely physical. X1, let me draw again, K1, K2, K3, K4. So this is y vector 1, 2. So this perimeter here is x1, and this is y12. So when I squash the triangle, it would tell me that the function blows up. Okay, so the boundary condition that there should be nothing special going on in this kinematics will enter in the actual solution. So it's related to Bunch-Davies vacuum initial conditions. But what I want you to capture from this first line is, you see, not any denominator. You could have gotten denominators that depend on x1, x2, and y12. They're generic, but the only denominators that appear are of this form. And you generated only one new function. Even though you have two denominators, you get back the wave function itself plus new function f. So now you continue, take dx1 of f, because you want the procedure to halt. So you're gonna get back, I think, I'm making it up, because I don't remember. Okay, so, but it's something, it's more like this, you get back f minus g. Now the denominator that appears in front of g is interesting. Of course, you should have complained, where is epsilon? Again, G is the integral of canonical form. That's why it's interesting, uniquely defined. But now look at the denominator that appeared in front of the new function G. It's x1 plus x2. You see I'm wiggling only here. I'm just shaking these 2 points. But now I managed to produce a letter that becomes singular when both energies flowing into the whole diagram add up to 0. So I explored this little vertex, and now I explore the whole diagram because it's the whole energy flowing into the diagram. So what will happen? Now I have new functions. So I must take a derivative of G itself, but now there's nothing else to explore. So I should get back. In fact, I do. I get back at G itself.
Can you drop up in 6-7 meters?
Yes. So the procedure hold. Now, well, I got 3 functions, so I got a 3 by 3 matrix doing this. But now I have to take derivatives with respect to x2 again. I just did from one side. But now it's not hard to imagine what will happen. So if I go from, I don't remember if this is a horizon. Everything is completely butchered by now, but
Yeah, we can move the camera.
okay. Yeah. If I do it from the x2 side, I generate, at first I'm going to generate denominators associated with exploring this vertex, x2 plus y12, x2 minus y12. And then I explore the whole thing again because I'm only coming from this side. And for the whole picture to be consistent, meaning for derivatives to commute, meaning if I take dx1, dx2, doesn't matter which order I take, I can't generate a set of 2 new functions. In fact, when I explore the whole diagram, I'm generating the same function g again. Okay. So I generate only 1 new function, and that gives me my 4-dimensional basis. And I'm done, the procedure halted. So this is completely systematic, and you can do it for any diagram. And it explains why life is so complicated when you act the middle. And it answers some amazing puzzle. Oops. That I had. I thought that it would be impossible, but I was wrong. So let me explain a slightly more complicated example, and then I'll stop. Let's do this diagram here. So what is the physical picture for what the differential equation is doing for you? The differential equation is, say, acting on the left, and through some series of moves, derivatives and yada yada, it's kind of acting on these vertices here, and because cosmology expansion is trailed by time evolution, I managed to engineer the Klein-Gordon operator acting on this vertex that collapses the propagator. Okay, so that's why the thing simplifies. Physically, that's what's going on. I generate a complicated operator that wiggles this guy, it generates Klein-Gordon, collapses it, and I have something simple, contact self-interaction, and then the procedure will stop. Now here, it's obvious that if I act on the left, the same thing should happen again. I take derivatives with respect to x1, y12, or y23. I take derivatives with respect to x1, and after taking a bunch of derivatives, it will collapse its propagator. I keep taking derivatives, I collapse the second propagator, the procedure halts. But what if I wanted to start from here? And I tried for a year. We tried for a very long time. Well, can you trade, just do this guy here and use these other variables? It doesn't work. Somehow, the systematic procedure makes everything work nicely. And the reason is that, well, as usual, physics is much smarter than humans. So what the x2 derivative is doing is it's not exploring to the left and or to the right. It's doing both at the same time. So if I take the derivative with respect to x2 of the wave function, I'm going to get on the right-hand side. Remember that I got the energies flowing here, but I can have minus signs. Now I'm going to get x2 plus y12 plus y23 times psi minus f1 f2 minus f3. And now I'm going to get stuff like this. I generate, instead of a single extra function, I generate 3 of them because I can have multiple minus signs. But other than that, it's completely systematic. And then I take these functions, and as I take x2 derivatives, I kind of grow the diagram in both directions. Eventually, I explore to the left and to the right, and the procedure holds. That's why the basis is bigger. That's why I need more functions, because it's going to be 16-dimensional here, because there are many ways of exploring the geometry of the Feynman diagram, and everything works out. So there's finally a way of spinning this backwards, meaning there is a completely systematic system of differential equations. And integrability of the system is very beautiful. It follows from locality of the diagram. So if these words intrigue you, you can ask me later, otherwise forget about them. So you can write down the system of equations and say that the solution is given by integrals. And this integral representation of the solution depends on a new variable, which is time. So it's not wired in, it emerges from the system of the differential equations. Okay, so to wrap up, this is done in a toy model. It's not relevant to inflation because I tuned the mass of the scalar. Redshifts away too fast. But I think it proves, or there's like some proof of concept, that there are a lot of techniques, methods from particle physics that make this like a very fruitful intersection of ideas. There are lots of ideas from both holography and from scattering amplitudes that comes in for this picture to emerge. And, exploring loops, exploring spinning particles, exploring masses that are not conformally coupled. All of these things, I think, are interesting and worth exploring. And the last comment, and I'll stop. You can, for example, in a planar theory, if you take these, for example, phi cube theory, and you give color to the scalar, there is also a beautiful picture for the sum of diagrams, meaning that the sum of diagrams solves a differential equation of a matrix A, which is not the trivial guess for what the matrix A should be, which is just summing the blocks for each individual diagram. So the diagrams share among themselves many entries of the matrix A. So the overall size of the basis is much smaller than you would have naively guessed. And then my final comments, if you're interested in what do these functions mean physically, are they just some crutch to get the differential equation for the original correlator? I thought so at first, but that's not true. You can do a simple basis rotation, and you can associate to all of these functions specific diagrams in which you include either a specific time ordering, so you make time flow, instead of doing Feynman propagator, you make time flow from the left to the right, or you collapse the diagram, you take the high energy limit. So you can do the counting, you see that you get the right basis size by this procedure. So I think it's, well, this is not entirely clean as of now, but it's clear that these functions are not just some crutch to give you the final answer of form psi. They have an interesting physical interpretation in their own right. So we'll stop here. Thanks.
Thank you. Standing up methods to get another section of gravity. Beyond.
Yeah, I think for actually spinning particles would be very interesting to extend by doing. We're not there yet.
Sorry, let me ask a question. Like, this is all much related to the system of canonical form, also in the biojoint cube you're talking about. So, since you're saying like there is a better way of handling differential equations for integral where they have this canonical form, so as long as you put that in such structure and you
Yes.
control the singularities, like then there is a kind of nice.
Yes, because the starting point is this final parametrization or this cosmological polytope way of identifying the integrals. For loops, part of the work is to bring the loop integral into the log form, right? And that's what requires some baking. Here it's automatic, it's wired in.
For the spinning case, do you have an understanding of the canonical?
Around the Sitter space, I think it's just a matter of technically doing it. I think we should be able to do it.
Okay.
Because there are weight shifting operators, there are ways of relating the scalar answer to the spinning answer.
Yeah.
And for this biojoint phi cube theory now, Nima, his collaborators, Songa and Carolina Figueiredo, I think they have a way of deforming the phi cube theory to get Young-Mills and GR in flat space. So obvious question is if we can deform this phi cube FRW wave function to get something related to Young-Mills or GR wave functions.
Maybe some double copy, I guess. Like.
It's something different. It's not. Yeah, I thought it was the scattering equation double copy, but it's something more straightforward.
Okay. So go ahead.
So the right hand side is 0 and epsilon equals 0.
No. Yeah, like good question. You can rescale. You can redefine f's. So, for example, in the system here, yeah. So when you set epsilon to 0, this vanishes. But then now you can rescale. You can redefine g tilde as epsilon g, such a way that when you set epsilon to 0, this vanishes, but this doesn't vanish. So you get some. You essentially kill off the diagonal, but the off diagonal stuff survives. So that's how you relate to polylogarithmic systems. Yeah, good question. What happens is that the integrals themselves, they have singularities as you send epsilon to 0. So if you redefine them, you get a nice system as epsilon goes to 0.
So let's thank Ian again. Bring to spend on the X and we reconvene. So I suggest 10 past with the dark.
You can see it on the way you